Hello, everyone. Wow, nice to see all these people here. That's fun. So before we get started, so my name is Sam. I'm a software engineer. I'm not a deep learning expert, so take everything that I'm gonna say here with a grain of salt. Don't believe anything I say. Just gonna talk about what deep learning is, how it's working. If you're scared about the maths, don't be. There won't be that much behind. So we're gonna try to see in reality what deep learning actually is. Just before we get started, I want to know who does big data here? I mean, who plays with Hadoop, Spark, all these kind of crazy things? Okay, not many people. Who calls himself a data scientist? I love this crowd. Nobody. I hate that word. Don't tell them. Yeah. Who here does machine learning for fun at home by night or just maybe somewhere? Okay. Okay, good. Not you. don't raise your hand. You do big data, right? Okay. So we're gonna stay a little bit above all the below stuff with machine with deep learning. So brace with me. So the talk was called Deep Learning for Mere Mortal, but I changed the name to call it a shallow dive into deep learning. Shallow in contrast to deep. I don't know who knows what shallow dive is, so we're gonna stay on top of the surface. So let's get going. Just for your own good, this talk is buzzword compliant. It has a lot of buzzwords. Many of them might make you sound pedantic at dinner with your friends, so if you want to use them later, be careful. So deep learning, if you look on Google, you see on Google Trends, from 2005 till 2014, I mean, almost nobody was looking at it. Nobody cared about what deep learning was. And yet suddenly, we've seen this growth of searches, so that's the growth of interest between deep learning. And it's prompted many people to actually wonder why. There's a reason, actually, there's this much interest into deep learning. In the same wave, we've seen scientific articles. I mean, those are scientific, those are researchers who actually publish a lot of papers, not just on machine learning, but specifically on deep neural networks. And this has skyrocketed in the past 2-3 years. I mean, it's almost as if the other part of machine learning doesn't exist anymore. Most people are actually publishing things on deep learning. So you might ask yourself, why? Well, in the same vein too, in the news, you see things like this. YouTube uses deep learning to pick video thumbnails, okay? So every time we go to YouTube, so instead of giving us a raw recommendation, they choose part of the video, they capture an image, they show it. So we can have an idea of what's in the video. And they use deep learning for that too. Good. Apple buys secretive deep learning startup because Apple wasn't secretive enough. So yeah, we're like, okay, deep learning is everywhere now. Microsoft is launching an API to track emotions, speech recognition. Deep learning again. Good. And you have these crazy things. Deep Dream, AI code. Who knows what Deep Dream is? Good. Some people are crazy enough here. Good. So yeah, we see a little bit what deep learning looks like. So basically, you're like, okay, since everybody's talking about deep learning, well, we better take care, we better look seriously about what this thing is. But before we see what deep learning is, let's see exactly a real application. I mean, you have many applications that we don't see, but let's have some fun. Just for the sake of it, I don't work for Microsoft, so I'm not affiliated with them as anything. There's this thing called Skype translator. What it does actually is that you have to, who knows what Skype translator is? Okay, well, Skype translator is actually you having a talk with someone who's speaking a different language, and you have the machine actually doing the translation. So I speak in English from my part, and you speaking in Dutch from your part. But you're not hearing me speaking English, but actually you're hearing someone translating in live translating what I'm saying in Dutch, and with minimum actually latency. And that's nice. So let's see what the video does.
The difference is the person you're calling doesn't have to speak your language.
Die ich dir gestern geschickt habe.
But I wanted to talk to you about the email that I sent you yesterday.
Brauchst du noch irgendwelche Änderungen?
Do you need any changes?
There was one thing though. Could you change the green to a lighter shade?
Könnten Sie das Grün durch einen helleren Farbton ändern?
Ja, wir können das Grün viel heller machen.
Yes, we can make the green much brighter.
Ich sende dir heute Abend eine neue Datei.
I'm sending you a new file tonight.
That sounds great. I look forward to it.
Das klingt toll.
With the Skype translator, it's a full human-to-human.
Okay, thanks, Peter. That's nice, but of course, Skype being Skype, it has to work first, so that's another story. But oh, come on, I'm just throwing some jabs. But that's really cool for me. I mean, I have many people who don't speak English or French that well, so sometimes they can speak in thing, and we have the Babel Tower actually for real. That's really cool, and that's something that really excites me. And let's go back here. Oops. So Skype, that's actually a huge problem they're solving, because what's happening behind is actually you have two things: speech recognition, so what I'm saying, and machine translation. And speech recognition is a separate field when it comes to machine learning. Machine translation is another one, so they have to do the glue between those two. And that's where deep learning actually is important, because speech recognition, you have a state of art that's now being based into machine learning as well. Machine translation have a state of art that exists already, but actually making them communicate this way live, that's a really breakthrough. Another thing is Google DeepMind. DeepMind was a startup actually that Google bought some times ago. And they do some cool things. Who knows Atari? Everybody knows, I'm sure. Yes. Who plays Atari still today? Shame on you. You're there. Okay, so they use this thing called Q-learning. Q-learning is an algorithm that's used in something called reinforcement learning. When we talk about machine learning, usually people say you have two classes of machine learning algorithms. So you have supervised learning and unsupervised learning. I'm sure at least all of you have heard about this. But there's another part that's usually forgotten. That's where the people who actually dream of robots actually guiding us next tomorrow actually try to work. It's called reinforcement learning, meaning that you're learning step by step of what you're doing. That's another part of machine learning, and it's something that's not really, it's a bit complicated. And it's used in things like when you're looking at a website, when you have to do A/B testing, you use things like bandit algorithms. So in the meantime, you can say, okay, I'm going to show this, I'll show that. You take that decision in real time. Those kind of algorithms are coming as something called reinforcement learning. They used to call multi-armed bandit. But the Q-learning is something different. So what Google did actually with Atari, the guys from DeepMind actually did from Atari, is like, they throw in something, they throw in a program that was actually going to learn to play Atari. It has no idea, no prior, no data, but actually learning from experience until it's actually going to be better, way better than a human being. So let's look, it's a 1-minute video, so let's look at this. Okay, it's self-explanatory. There's no domain knowledge from the very beginning, so the algorithm doesn't know any concept of ball, of all the play. So 10 minutes of training, it fails miserably. Just look. Tac, learning. Okay, has no idea what it's doing, so yes, let's move around. Let's try to build, okay, that's what it's doing, just like a human being, actually like a child. Oh, there are balls coming, can I catch them? Oh, so I can do that, fine. 2 hours later, it plays like an expert because it knows, oh, I can kick this ball out. Duk, 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 duk. Good. But it's still failing, right? Some balls are, so it's not catching everything. Tuck, 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 tuck. Go, go, go. Okay. Fast, 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 fast. 4 hours later. Now, yeah. What's he gonna do? It's already very good. Yes, now it's kicking us at this game. So yeah. Bam, 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 bam. Well, now it plays better than a human being. Doesn't matter what expert you are, it does the magic on top. So yeah. Yes, this is deep learning behind. So that's reality. That's a paper that's been published not so long ago, and they have this. The code is available, of course. I mean, you can play with this kind of thing. This is real deep learning. This is machine learning for real. So now that we've had some fun, let's go back to shady things. Deep learning. So now we've seen all the cool stuff. So what is it exactly, deep learning? I mean, everyone has its own definition of what deep learning actually is. I mean, when you ask someone, you say, yes, it's like playing with non-convex transformations. Yes, I mean, bringing something different. So the way we can define deep learning is actually, it's not one algorithm, but rather than a set of multiple algorithms. What they do is that they take high-level abstraction. So for example, I'm speaking. What it's going to do is that from representational data, that from my speech, what the computer is going to learn is that those are actual numbers. It's going to learn some representations and actually learn again by adding multiple hierarchy of learning. We'll see how it goes. So they're usually built using neural networks. We'll see what neural networks. I'm sure everybody knows, but who knows what a neural network is? Good. Who knows what a perceptron is? Okay, good. Who knows what a recurrent neural network is? Yeah, those are a curious guy. Good. And the same thing happened, and deep learning is actually about learning representations. We'll see how it relates to what we do in common machine learning tasks later on. So when we do machine learning in reality, you don't just take your data, throw in the algorithms, and wait for a result. That only works on Kaggle. But so if you go beyond Kaggle, that doesn't work. But the reality is that you have a lot of data. That data has to be fed into the algorithms, but you don't feed that data as it is. It's not raw data you're actually putting into the algorithms. You have to learn features. Features, that's where the domain knowledge comes in. So those features, you create vectors over there. You feed them into your machine learning algorithms. That's called the training part of the algorithms. From there, you can add labels. Labels actually telling the algorithm that, okay, this data represents this. Actually, you're building vectors with this kind of stuff. And then once you have trained your algorithms, what you're going to do is that from new data coming in, it's going to do some transformation based on what it has learned from previous data. That's what a normal machine learning algorithm is. But the real job actually happens here, because for that, you have libraries. When you do machine learning, well, if you do Python called use scikit-learn, I don't know, predict, give me a logistic regression, you're going to give something. You have algorithm for this. For that, well, libraries do that too. But here, that's where the magic happens. That's where the real complication actually is, because you can't automate, or you can always automate this kind of knowing from your data. If you're reading text, you're not going to interpret text the same way you're going to interpret images. It's not the same thing. So you have to have a base knowledge. You need to have a business knowledge or a domain knowledge to actually create feature vectors. So you're doing feature engineering. You're trying out some combination. What kind of feature is going to be okay? Which one is going to work? So let's take an example. For example, face detection, face recognition. What you're going to do is that you have a frame of picture. You want to detect the face. You're going to find where the face really is. You're going to extract the features. Now, it's an image. What you're going to use are pixels. Those pixels are going to build some vectors, and those vectors are going to be computed to do something else. And you're going to train here down below. You have a database of data where you train all your features from multiple images. You create multiple vectors. From your learning and your algorithms, you're going to have to create a classification engine. So for every new image, you can compute the same thing. It's the same thing as here. So the real problem, as I said, is here. So what deep learning wants to do by doing what I call learning representations is from every kind of data, automates the learning of those representations, and by doing multiple hierarchies, knowing exactly what my data means, what this representation, and actually automate till the output. That's the magic, and that's really complicated to do. I mean, that's really complicated. It was really complicated to do until recently. So to do that, the deep learning use, of course, neural networks. So what are neural networks? Just a little bit. This is a brain neuron. We usually say that, yes, a neural network is like a human brain neuron. Yes, not quite. It's an imitation of this kind of thing, but it's not really that. But yes, what you have dendrites, synapses, and you want to plug these signals coming in, and you have a function that's gonna go. Well, we map this way of thinking into what we're going to do. This is called a perceptron. So you have multiple signals coming in. You have an activation function. You have an activation function, and the activation function is going to give you an output that's computed by function. So the first version of neural networks come from the 50s. So it was called a perceptron. This is what it looks like. So a perceptron has multiple inputs of data coming in. You have a transfer function that's the sigma there. I stayed a little bit light on the mat. And you have a function that's going to activate this neuron. And from that function is going to have an input. And that input is usually computed using a function that's known for many people that's called a sigmoid. This is the function down here. This is usually how a perceptron works. And the output error is computing by using this formula. And the goal of every machine learning algorithm is to minimize your cost function. So to do that, what they use is stochastic gradient descent. Who knows what an STD is? Okay, some people, I'm not gonna dive into the real formula, but basically a stochastic gradient descent is a way to actually minimize the global error of your function, because these are all approximations. So you want to have this thing to fit together. So you're going to minimize that error. So you use things that comes from linear programming, like stochastic gradient descent. And since that error is going to propagate through multiple levels, you want that error to be caught somewhere by using something called backpropagation. So when you don't want to do the computation from the first level here, but you actually want the error to be managed from here, and then you throw it back behind. That's what's called backpropagation. And backpropagation is actually a way to minimize error by changing the weight between your neurons. So to do that, what we have here is an example of what you have with a regression. I think we all know what a regression is well, on the image over there on the left, what you have is a typical machine learning regression. So you see that you have a huge error, because even for you, it's hard to generalize actually your algorithm with this, because you have all the red points and the green points are actually scattered around. So to find a proper function to do the prediction of this is really complicated. In a neural network, since it's using nonlinear functions, so you can see all the things dancing around, it's not convex. So you're going all the way around, but you have things that are separated correctly. So that's one of the advantages. But this in machine learning causes some problems. We see why later on. So you have one neural network, that's the perceptron, but what you want actually later on is actually from one layer, only one layer of perceptron, you want to learn multiple things. So you're going to add over layers. So this is a multi-layer perceptron. It's also known as a feed-forward neural network. You're adding layers, so you can learn representation step by step. So you have data coming in from an image. You want to learn representation from those images. Okay, is that a head or, I don't know, a bag? Well, you have one way to learn that bag. You add another layer that's going to learn, and you're adding layer. Those layers, well, that's what's started to look like deep learning. You're going deep into your layers. But that's costly. That's a problem. That's actually been for a long time the real problem. So what do you call deep? Usually you say you deep once you have something close to 3 layers, once you go beyond 3 layers. You have other algorithms called like SVM, support vector machines. They're not deep. They behave a little bit like this, but they're not deep. But when you start to go beyond 3 layers, you're starting to encounter the problems that has been plaguing the neural network community for decades now. And why? Because your gradient is a function that keeps going, and you have this problem that your stochastic gradient descent is disappearing. It's used to call the vanishing gradient. We're not going to dive into those kind of things, but if you want to see here, within the neural network, you see that you have all these things that actually just take the red dot. So it's doing some circles around the data. This is overfitting. This is something that's a problem in machine learning because you cannot generalize this kind of problem. If you take your training data, the images from on top of which you have trained your neural network, well, when you've trained the data from which you've trained your neural network, if you want to have prediction from new data, it's not gonna work because it only knows the data as it is. It cannot generalize. That's the real problem with machine learning, and especially with neural networks. So it's hard when you're starting to add big layers. Well, that starts to become issues. And you can see here, when you have one neuron and different layer, it seems to be that it's overfitting, it's closing, it's chasing actually all the data where it is, which is good in a normal setting, but it's hard to generalize for new data. That's things that actually led to what we used to call the AI winter of neural networks. So it's been some times where people were like, neural network are dead and not working because you can't do much with it. That was in the 90s and some over years. So after the AI winter, the first one was in the 70s, I think. I don't recall properly, but in the 90s, you had things called convolution network, and then it died again until in 2010. So this is a little timeline from the perceptron, how the neural networks evolution community has evolved to new things. But what's actually striking is that you had the same thing in 1999 by Yann Lequin. That's a French guy who leads the Facebook AI research laboratory, the AI research lab in New York. But he's the one who actually managed to use things called convolutional network for handwriting and image recognition. We see what convolution networks are. But that's in the 90s. And somehow people forgot about them. You had SVM, logistic regression. Those were the new things in machine learning. And suddenly, in 2006, you have this thing called ImageNet. That's a competition. Well, ImageNet, you had Geoffrey Hinton. That's the guy who's been working frantically on neural networks since the 70s, who actually went down and they won the competition by by adding new techniques to actually compute gradient descent, to do this kind of, to have neural networks that actually work. That was in 2006. And in 2012, Jeff Dean, that's the dear God at Google, he actually manages to bring neural network to actually train them in a distributed fashion. That's hard to train this neural network in a distributed fashion. And that's where actually you've seen all these frameworks, all these elements coming out of now Google, of neural networks, because Google actually went in deep and they published a lot of papers. Other people followed suit. Microsoft have been working on it for a while now. But Jeff Dean actually, they put a lot of deep learning knowledge into Android speech recognition. When you use Google now, you're actually using a lot of deep learning systems that are trained in behind. When Google now is actually telling you in the morning, okay, you're so late, but you have to take your bus at this place unless you're gonna miss your plane. So it actually guides you. There's a reason for that. It's working on so much data, so much inputs, but they have systems that are trained so well that you came up with actually accurate results. And they keep publishing a lot of things. And one funny thing that came out of Google a few weeks back is actually the auto-reply thing. That's they're using NLP. So from your email, from your previous email, Google Gmail is capable actually replying at your place. So you say, okay, I don't want to talk this paper. You activate the thing, and Google says, sure, I've read that. I'll call you back in 10 years, so come back again. So and I've been dreaming of having the same thing for Slack, because Slack is good, but still. That's a digression. So let's go back to neural networks. So Why suddenly in 2006 it started working? Well, first of all, because you had some clever new ideas that went into developing these algorithms. And one thing that changed is that, well, it's Google, it's all these people, we had a hot load of data. You have a lot of data. I mean, we spend so much time on the internet now. I mean, I'm not gonna give you the big data gospel here, but we all throw data all the places. So there's all the places you can pick up data. So that's what makes the difference. And the other thing is that you had more compute power. Back then, when you had one computer, it was, yes, great. You want to train a deep neural network? Well, buy an entire building. Now you don't have to do that. But yes, CPU are great, but not that great. So most of the deep learning work tend to work on GPUs. There's a reason for that, because computing gradient descent is a highly iterative thing. You can parallelize that. You have a lot of ways to do that, but gradient descent usually work only on GPU, work very well on GPU. So that's why you see a lot of work that actually goes into GPU. So convolution networks. Let's go back to this thing. We see something like 2 examples of this, and then we'll chat a little bit. Convolution networks. What are convolution networks? Well, basically what you have are images. When you have images, here, let's say Albert. This is Albert Einstein. You have images, you have pixels. From these pixels, you have weights. So you have inputs, you learn from those inputs. And from those inputs, you have these pixels, you have vectors. On these vectors, you want to pull them together. So you have what's called share weights. Sometimes you call them taking pools of your data. So you want to capture the context, not just this vector alone, but what's around him, and try to learn what you have. So this, what's called convolution network. So in order to make it work, you have things like feature maps. So you map all your elements, you separate all your images, you actually exploding all the features that you have, so you can learn them in a very different, in a very high context. And then you apply a different set of transformation. So you're adding other learning layers. Let's see how it works here. Those were convolution network in the 90s. So as we can see results, they could recognize handwriting quite easily. That was okay. So that's why banks actually were working to recognize, yes, I'm signing this check. So these were the kind of things that you already have in. It's not perfect, but yes, it was already getting in. That's good. But in the 90s, what came up is actually a way to learn multiple layers, like we talked. So we take this picture here. It's actually the same that's showing up here. This is actually what the math looks like. So you have these different sides where you're going to learn. You have different functions. Those are tangent. I'm not going to dive into this math. But just to give an idea, you have pixels that are coming in. You convolve them. You're actually exploding them to different feature maps. And then from those features, you have different learning layers. And you have transformations. Some of them are called max pooling. And these are formulas. And you're pulling all those learning layers together to have actually a proper result. So I'm not going to dive into the thing, but just to give an idea, this is how it works. And in 2006, ImageNet used this thing, convolution network, trained very well to actually win the competition. So what they did is actually not just taking images, but actually from an image, inquiring what the image is actually describing. So you can see that you have a container ship. By learning from a bank of close to more than 1 million images, learn from them, they could actually manage to infer that in that image, it's a container ship. And that was in 2006. And what they did is actually, that's what they did with using just convolution network with some tricks to make it work, using things like restricted Boltzmann machine and a lot of other things actually. Those were CNN, so that was really nice. That's actually started the deep learning wave that we're still living now. Other type of neural networks are recurrent neural networks. Well, recurrent neural networks are a bit interesting because what they do is that they have an internal state on top of from which they can learn sequential kind of data. And that's interesting. For example, we live in a world where you have disconnected devices, IoT data. So this IoT data actually, you have time series data coming in, especially within, and you have speech recognition as well that can be modeled as time series data. So using this recurrent neural network, they work very well. But the only problem is that if you remember the diagram of actually neural networks, you can propagate only going forward. I mean, you can go back, but you can go back so far because it's losing its state. So that's a bit of a drawback. And another thing that's actually trying to solve this problem is things called long short-term memory neural networks. It's called LSTM. This is a good thing. This is things that are coming over to, for example, for sentiment analysis that you're using this kind of thing. And there's a lot of work going in. And this is really good for NLP. And you have a lot of paper now, a lot of papers that have been published for this. And to illustrate how it works a little bit is that let's see this as being layers. So you have one-to-one layer. As you see, they're not really going back. It's hard to propagate back. It's only going forward. These are kind of recurrent neural networks. These are different set of architectures. And some results, like we saw before with ImageNet, so we have this, you could infer what the images were, what image we had inside. But combining convolutional neural network with recurrent neural networks, well, we end up with things like this. You can describe properly, not just with a single word, but actually inferring what's really happening. And this is not just saying, okay, there's a guy, that's a container ship, but you say exactly what the guy is doing. That's multimodal. And this was a breakthrough was not so long ago. So they're mixing actually visual and semantic actually alignment to actually give a description to a picture. You're not just auto-tagging a picture, but actually giving a full description to your picture. So here, for example, you have a baseball player is throwing a ball in a game. Well, that's automated. And the same thing goes over there for the boy is doing a backflip on the wakeboard. I couldn't have imagined that a computer would do something like that. I mean, okay. That's good. Some humans can even recognize this, so it's nice to see. And you have a lot of other deep neural network algorithms. You have autoencoders that actually do compression of your data, so you can produce different new encoders. RBM, deep belief, that's what you really have at Google now. That powers most of the Android things. These are different. A lot of other deep neural network algorithms out there, and I don't know if it's clear. This gives an idea of what kind of algorithm you can use for deep learning. Each deep learning algorithm over there can tell you if you're dealing with text, for example, sentiment analysis. Well, you can use deep belief network or recurrent neural network train over there with moving windows. So that's the kind of algorithm. So this gives you an idea what kind of algorithms you can use. For images, for example, well, deep belief network, that's what you have on Google Photos, on Google+. This is the kind of thing that you see there. To recognize objects, that's the same thing. And for voice recognition, well, you use recurrent nights. Same thing for time series and for predictive analytics, for example, with or something like anomaly detection. Recurrent neural networks really work well for this kind of things. So this is a nice thing, just a reminder to find out what you're going to do. And there are a lot of actually libraries out there that you can use to work with neural networks. So let's look at how you can use neural network in your thing. I'm not going to give the code or something, but there are a lot of frameworks, a lot of libraries for neural networks. Most of them actually usually came from academia. So you had this tiny thing over there, but hopefully you have a huge open source community, but not much on the JVM. I know we are at Devoxx, so this is a mostly JVM focused conference, and I think the crowd here is too. But yeah, most of them actually come from C++, from Python. Why? Because it's way easier for them to work with GPUs. And most of the neural network algorithms actually work well with GPU, like I said. So a lot of work has been done that came out actually from in the Python community, because they do a lot of machine learning, in other communities as well. One of them is Triano. Triano, that's a Python library that's really used. It's open source, of course. The other one is Torch. This came out from Facebook. And the Torch guy and the Triano guy hate themselves quite deeply. I still don't know why, but you have religions in technology, right? So Torch is built with Lua. So if you're into Lua, and it's really fast, it's really, really, really nice. You have a lot of library, a lot of things to learn. You have Cafe, that's from Berkeley. That's something you can try too. See if you're into C++ and Python, that's nice. And on the JVM, at last, you have something like H2O. H2O is a machine learning library for common machine learning library, and they have some algorithm for deep learning. And the good thing with that, if you're doing Spark or Hadoop, is that you can use them on Spark as well. So you can distribute your computation using H2OI. That's nice. You have a lot of things you can try there, but it's really neat. And the other one is deep learning for J. That's it's done by a company called SkyMinds. So they call themselves the enterprise deep learning. So you can use that with Spark 2. It has some binding in Scala. It's written in Java, of course, hence the 4J over there. It's a nice trick, and the picture that I had, the matrix there for all the algorithms came out from their website. So it's something very nice to look at. So yeah, you can try that. And there's the new one that came out earlier this week. That's Google, TensorFlow. And this, I think, it's really neat because it changes a lot of things. It's in Python, of course, fortunately, if you're doing Java. But it's really nice because you have all you need to build an application. And it's really well thought. The API is clean. It's something, if you really want to try deep neural network, try TensorFlow, just to have an idea, read a few things. But TensorFlow is actually nice. So it's nice. It's really nice to see how the other libraries will compare and try to evolve from this. So if you want to get started within machine learning, I advise you to go on Coursera. There's a great course that's been there for a while called Neural Network. It's given by Geoffrey Hinton. That's actually the guy who's been working on neural network for a long time, and he's the guy who won the 2006 ImageNet actually competition. And the course is really great to get started to learn a lot of things, not just on the basics of neural networks, but also on deep learning, because the guy is an expert. So it's nice. Go on the deep learning 4G sites. You have a lot of resources there to get started, and look at deeplearning.net. You have a lot of maths at deeplearning.net because it tries to give you all the foundation actually to come up with machine learning and deep learning. But it's really nice to see. That's all I had for me. Thank you. There's a lot of time for questions, so if you have some, feel free to shoot. Questions? Yeah?
So one of the properties of neurons in the brain is the timing.
Yeah.
Like if the impulse arrives before the neuron fires, it gets stronger.
I think there's a mic over here. See if you can come. I can't hear with people like. Okay, that's fine. Okay, thank you.